So question 95 is asking, or it's giving you a couple of things right off the bat, which is it's telling you that water and ether are immiscible liquids, which is basically telling you that you have kind of an oil and water kind of scenario going on. So if you took a liter of water and if you took a liter of diethyl ether and you mix them together, you would actually get no mixing at all. You'd actually get this cool little layer in between the two, and you'd be able to partition stuff in between the two layers if you really wanted to. But then it gives you this kind of precondition, which I want to talk about just for a second. It tells you that charged compounds dissolve in water and uncharged compounds dissolve in ether, and this is true to a degree. It's actually not true all the time, but it actually is a pretty good generalization. So if you want to use this as a general rule of thumb, 99% of the time you'll be correct. But just make sure that you recognize that this is a gross overgeneralization. But it's good enough for what we're going to try to do in organic and in the organic lab. Okay, so let's just go ahead and proceed as if this was always true, and then we'll talk about exceptions as they come along. So let's say charged compounds dissolve in water, uncharged compounds dissolve in ether. Okay, and then, so it gives you these two compounds. It gives you this carboxylic acid, and it gives you this ammonium compound. So it gives, some other bits that are tacked onto it, but I'm not really, those are very unimportant, so I'm just going to represent those as generic R groups. So again, these R groups just say that there's something attached, but whatever it is, it's not that important to answering the question. We could always say R equals whatever later on. Okay, so our carboxylic acid has a pKa of, again, 4.7, 4.8, somewhere around 4 or 5. The ammonium has a pKa of around 10 or 11. It does not have a pKa of 40, again, because now this nitrogen is charged, so that's going to totally change the pKa. So, in this case, we're going to have one compound in the water layer to begin with, and one compound in the ether layer to begin with. So, see if you can figure out which one's going to be in the water, which one's going to be in the ether. Okay, so this guy right here is going to be in the ether layer, and this compound down below, this ammonium, is going to be in the water layer. Okay, and the goal is to say what pH do you need to make that water layer to cause both compounds to dissolve in it. So basically it's asking, how basic does your water need to be to cause this carboxylic acid to become deprotonated? Okay, and so do you remember the rule for how we figure out at what pH a compound will become deprotonated? Let's take a second, pause the video, see if you can remember. So again, the general rule is that if the pH of your solution is less than the pKa, that compound that you're talking about is going to remain protonated. And if you are able to get a pH that's higher than the pKa, then that compound will become deprotonated. So again, what we'll want to do is we want to deprotonate that carboxylic acid. So we need a pH that's higher than its pKa, but we don't want a pH that's higher than the pKa of the ammonium, because then we might end up deprotonating it and it'll become transferred into the ether layer. So we got to walk a fine line. Okay, so let's talk about each particular scenario. So we'll go with 3 different scenarios. One, if we have a pH that's less than 4.8, and we'll just work our way up. So, what if the pH was 2? And we've already said this is not what we want, but let's just go through the scenario and see what we get. So, if we had a pH of 2, 2 is going to be less than the pKa of the carboxylic acid. It's going to remain in its protonated form. Okay, and 2 is going to be a lot lower than the pKa of the ammonium. So then the ammonium is going to remain in its protonated form as well. Okay, so now what we have is still that ether layer, and we're still going to have water soluble ammonium. Okay, so that's one scenario. And then if we have a pH of somewhere in between, so let's go with the scenario that we said at the very beginning. We know that we want to have a pH above 4.8 and somewhere below 10.7. So let's just, arbitrarily say pH of 7. If we had a pH of 7, the pH is going to be higher than the pKa of the carboxylic acid, and so now it's going to become deprotonated. So it's going to lose that proton as H+, and again, you need to make sure you balance equation or the charge on either side of the equation. So if we know that we started off with a neutral compound, we know we're losing an H+, that must mean that overall this compound becomes negatively charged. So we go from the carboxylic acid to the carboxylate, and the carboxylate is now charged, and according to that rule, that generalization that we said at the very beginning, that charged compounds are going to dissolve in water, we can now say that this guy is going to be water soluble. So pretty easy. And now, going from 2 to 7, let's see if that actually changes the ammonium charge at all, or its protonation state. So if we're at pH 7, this is still way lower than the pKa of the ammonium, and so we're not going to be basic enough to deprotonate the ammonium. So it's going to remain just the way it was. It's going to remain as NH3+, okay, and it's going to remain water soluble. And now let's see what happens. Can you predict what we need to do to remove the proton on this NH3+? So take a second, pause the video, see if you can figure out what kind of conditions we need to change this from being positive to neutral. Okay, so we've basically run the gamut of really low pH to really high pH. So let's just keep on going up. So we know we've already fulfilled one scenario of having a pH less than the pKa of the ammonia. Let's do what if the pH was higher. So let's say what if the pH was, I don't know, something about 12. Then if the pH of 7 was basic enough to deprotonate the carboxylic acid, it'll be more than sufficient to deprotonate it in this scenario as well. So we'll keep the carboxylic acid deprotonated, and it'll remain as the carboxylate, and it'll remain in the water layer. And thinking about the pH versus the pKa of the ammonium has a pKa of 10.7, so we finally made the solution basic enough to surpass the pKa of the ammonium. That means that ammonium is actually going to lose a hydrogen, or a H+, and so that means we have to balance the equation. So we start off with a positive on the left side of the equation, and we end up getting, let's say we start off with this guy, and we know we're going to get an H+ on the right-hand side of the equation. That must mean that our ammonium can no longer be charged, because we have to have that charge balance. So we're going to have the H+, and we're also going to have NH2. Okay, so now we know we're going to have the ammonium switching over to the ammonia, okay, or the amine, and now it's no longer charged. So according to this rule that we said at the beginning, an uncharged compound will dissolve in the ether. So that means that this compound used to be soluble in the ether, but now that it's no longer positive, it's going to be, it used to be soluble in the water, but now that it's neutral, it's going to be soluble in the ether. Okay, and so really we've actually already gone ahead and answered the sub-question B and sub-question C. So to answer A, what we need, a pH that would be sufficient to make both compounds dissolve in the water would be about pH 7. If you wanted the acid or the carboxylic acid to dissolve in the water layer and the amine to dissolve in the ether layer, we'd need the pH to be about 12. And if we wanted the acid to dissolve in the ether and the amine to dissolve in the water, we would have a really, really low pH or really, really acidic condition, such as up here in little Roman numeral 1. Okay, so really, really low pH. So just by going through a couple of those different scenarios, we've shown how we can actually move compounds from one layer to another. And this is actually kind of a really neat mental exercise, because we'll be doing this in lab, and you can actually utilize how, this drastic change in solubility to separate compounds. And it's used all the time in industry to separate compounds from each other. It's a very simple way of doing it.